Yeah, okay. Yeah, so yeah, our first speaker is Professor Andrea Vedaldi from University of Oxford. And Andrea is a professor of computer vision and machine learning and a co-lead of the VGG group at Oxford. He is also the leading author of the VLFeed and MetCompNet computer vision and deep learning libraries. Okay, yeah, let's welcome Andrea, and you can take the lead. Yeah.
Hello, thank you for the introduction. So let me just make sure my slides are working. I guess I need to share my screen somehow here. Okay, so let's see. Are you able to see my slides?
Yes.
Okay, excellent. Okay, thank you for the introduction again. So it's a very real pleasure to be here to talk to you about our recent work in 3D understanding in Facebook. So the workshop is about filling scenes, but my talk in particular is going to be focusing on a subset of scenes, which are objects. Okay, so why is that? Well, suppose you're given a scene like that. Of course, you would like to be able to interpret that in 3D, but if you're just given a single image, it's actually a task which is essentially impossible. You need to have prior information that allows you to take that image and give a three-dimensional interpretation or reconstruction of it. This is particularly true for small region and background, where you as a human can see that those are, that's some fruit, maybe some apples, and so you can engage your mental prior of what a piece of fruit actually looks like, and with that you can get an estimate for the 3D shape, which is likely to belong to that region. But for a machine without priors, that this would be impossible, of course. So our goal here really is to inject somehow in our machine learning algorithms enough priors, 3D priors, in a way that this would be sufficient to take an image like that, which doesn't really contain a lot of information, and extract instead of 3D reconstruction, which is at least plausible. Okay, so today I'm going to discuss three things in particular: data, representational learning, and correspondences. Okay, so this is the menu, and I'm going to start with data. Okay, so if you look at which data is available to us as a community to learn about 3D object categories, so what do you have there? Well, you have large data sets of synthetic data, like, for example, ShapeNet. Now, that's great because this data is perfect, right? It's very clean. It's actually quite large. You have all the information you require to supervise your algorithm and get something done. The downside, of course, is that this is synthetic data, which means that if you just learn from ShapeNet, it's difficult to just by having done that, have something which is sufficient for interpreting the real world. On the other hand, you could have real data sets. We have plenty of those in Vision, CAD, Pascal, and so on. Now, those usually come in the form of single images. And there are a lot of models that have been looking at the problem of taking these data sets and trying to infer from these single images some 3D information, all right? Trying to reconstruct the categories which are these images and extract these priors automatically. Now, this is possible, but also very, very hard, because this data essentially comes with single use, no annotations, no information other than one single picture per object instance. Okay. So what we're going to do today is going to introduce a new data set, which we call Common Object in 3D. And this data set is going to contain videos of objects. So you can see them from multiple views. But these objects will be real. It's not like ShapeNet, in which you have CAD models. This is actually real data collected in the wild. All right. Now, this video is just a short introduction to what this data set looks like. So you see here on the left some of the videos which I've captured, and on the right some of the 3D reconstruction we have obtained. So this is a relatively large data set. As you're going to see, contains about 19,000 different videos of objects from 50 categories that we have subsampled from COCO. All right. So that's why these are called common objects. Stuff, for example, like teddy bears. In addition to having the videos, we also have with them some 3D ground truth that we have reconstructed from the videos as well. And we're going to discuss what that is, what are the limitations, and what are the advantages of using this data for learning. So again, this is common object in 3D. And so what's the content of this data set? Well, this is a large collection of videos that we have crowdsourced from the internet. All right. So actually, you can think of that as a sort of reverse labeling process. So you go to Amazon Mechanical Turk and you ask people not to label data that you have, but rather to collect data based on a label you give them. All right. So for example, we ask them to collect videos of apples, and we explain to them how they should be doing it. So rotate around the apple so we can see all the views. And well, of course, there are more rules than that, but essentially. And so what you get out of that is a video which looks a little bit like a turntable, all right? And given that, then you can automatically reconstruct quite a bit of information. So you can run structure from motion and other methods that we're going to discuss in a minute. So you can get back the cameras, and you can also get back a segmentation of the object and a 3D reconstruction of the object. Now, once this is done, you can use this for training an algorithm. Okay. Now, this is an example of the data we have collected. This is broken down by categories. So this was an initial collection of about 30,000 videos. This is just to give you a sense of which categories came back more frequently from Amazon Mechanical Turk and which ones are less common. For example, it was pretty easy to get videos of carrots, but a lot harder to get videos of TVs for some reason. Okay. And these are some of the videos we have collected like that for two categories, teddy bears and hydrant. And of course, there are 48 more. So this is a comparison of our data set compared to what's out there already available to you. What you see here on this graph is a summary of how many categories there are in these data sets and how many objects there are in these data sets, so object instances. All right, so for example, on the left, you see that ShapeNet is very rich. It has many categories and many instances per category. Other data sets, but of course, it's synthetic data, so it's not real. Other data sets might have real images in them, but they don't have as much variety as we offer with the common objects in 3D. Okay. In terms of ground truth, what we have are a reconstruction of camera motions, which work very, very well. And for a subset of the videos, we also have a reconstruction of the dimensional shape of those videos that you can use, for example, for evaluation of your reconstruction method. So how do we get these reconstructions done? Well, we use essentially a classic pipeline, which is largely automatic, and there is a little bit of manual checking to make sure that things are working properly. So we perform essentially two steps. One is we apply structure from motion to get the viewpoint out from these videos. And then we use density reconstruction, which also comes as a byproduct of, if you like, modern structure from motion packages to get the point cloud that approximates the object surfaces. So here you see an application of Kodma, which is a standard package for structure from motion applied to one of those videos. You notice that despite the fact that there aren't really many features except the object itself, is just a white cloth in this case. Kodma is perfectly able to track the camera, and this is true for the vast majority of the videos actually. Once you have that, you can then perform 3D reconstruction. All right. Now this is not super fast. It takes about 30 minutes to process a single video, and to collect these data sets, we required 40,000 GPU hours. So it's not something that you can easily do yourself unless you have this kind of hardware. So of course, not all videos work out of the box. At the end of the day, this is Kodma, which is great, but it's not going to work for all possible videos you can throw at it. Nevertheless, if you look at the statistics, you'll see that, in fact, it works for the vast majority of the videos. So there are less than 4 or 5% of the videos where Kodma has a problem. But this is only for reconstructing the camera motion. The other thing you need to do is also to reconstruct the surface of the object, for example, because you might want to have a sort of pseudo ground truth against which you might want to compare your own reconstruction method. Okay. And so this can also be done using something which is embedded in Kodma, which is essentially stereo. And it works fairly well, but not for as many videos. So this information is only available, again, as I said, for a subset of videos that we use for validation and testing. Oops. Okay. And so here you see some example of 3D reconstructions you've got by doing this. And finally, a slide that summarizes how many videos we started from, how many survived structure from motion to the point of estimating viewpoint, cameras, and then finally, how many those also have accurate enough point cloud that you can use as a reference for reconstruction. Okay, so that's common objects in 3D. And this data set is going to be available, I think, probably next week, or maybe in at most, I would say 2 weeks' time. We're just cleaning it up and making it ready for download. Now, what I would like to discuss next is some method that you can actually train once you have data like this, all right? What can you do once you have this data? How can you learn priors that be useful for object understanding and scene interpretation once you have the data set like that? So I'm going to discuss a sequence of 3 problems of increasing complexity. And the first one is actually relatively straightforward. Still not easy, but by comparison, it's much easier. So here the point is we have a single video as input, okay? And the goal is to do a single reconstruction. So we want to have a single video as input, many viewpoints, and the goal is to just produce one reconstruction, which is essentially what Kodma does, but we want to do it hopefully better, okay? So how can we approach this problem? Well, you're probably already familiar with techniques that can do that, for example, Nerve. So the basic idea is you're going to get your frames, you're going to extract one of them, you're going to have a camera, which is looking at this object, which is given to you, actually, because this is part of the ground truth that we give to you with the data set. You're going to initialize some 3D model of the object, which is not going to look as good initially, but eventually, once you have converged, will probably look like an apple in this case. And with that 3D model in the camera, you generate an image, you do a comparison between what you've got and what's the training image, you measure some photometric error, and you minimize that. And maybe you minimize some other meta information as well, for example, a mask of the object. In this case, we're interested only in reconstructing the object, not really the background. So for us, masking the background makes a lot of sense. Okay. So that's the basic idea. That's very simple. And essentially what you do is you throw this into an optimizer. You have a model which is learnable, minimize the loss functions, you get a reconstruction out. Now the issue is which representation are we going to use for modeling these objects? And here there is an ample choice of things you can pick from. So you have implicit function, for example, opacity-based, sand distance-based, or you can even just learn to remarch in the volume without even having an explicit representation of the space where you perform this remarching for the purpose of rendering. Or you can have more traditional representations, like, for example, voxels, meshes, or point clouds. So the first thing we did was to take this first problem, which is the easier one, so just to reconstruct a single video, and we want to benchmark all these different techniques to see which ones would work well for this kind of objects, all right? Now, that should not be surprising to you. This is the same problem that Nerve solves, neural readiness fields. There is a reason why this method is so popular. It works very well. And in fact, for this particular problem, Nerve is the one that works the best, okay? And at least we're concerned perceptual metrics, like, for example, PSNR and ellipsis. Yeah, sorry, LP-IPS. However, this is not necessarily always true. There are other techniques that are also very competitive. For example, IDR. So the main difference between, well, a difference between Nerve and IDR is that Nerve uses an occupancy field as a representation of your 3D shape, and IDR uses a sign distance function instead. Okay. We also tried to port some of the techniques from Nerve, not just a sign distance field, but Nerve has other ingredients that make it work well. For example, this idea of positional encoding. We ported them back to the other methods to see whether they would also improve. And actually, that's not necessarily the case. Very often, if you inject positional encoding, for example, in a method that uses a sign distance function, that would actually lead to overfitting. So it's not plug and play, as you might hope. Generally speaking, the implicit methods, whether they're based on sign distance function or whether they're based on occupancy fields, they tend to beat methods that are based on meshes or point cloud by quite a margin. Okay. And well, that was at least in terms of perceptual error when you're trying to reconstruct the video from a new viewpoint, or the object from a new viewpoint, how well you do. In terms of depth reconstruction or reconstructing the shape of the object, similar conclusions can also be drawn. Okay. However, when you look at the big picture here and you look at how slow these methods are and how well they perform, okay, and also how difficult it is to train them, well, then the picture actually changes a little bit. So as we said, methods that use this sort of implicit representation, they tend to perform better, they're more accurate, but they're also extremely slow. So if you take something as simple as neural volumes, you get something which actually works a lot, well, almost as well in terms of many of these metrics, but it's a lot faster to train and also to evaluate at test time. So, if you want to go for full quality, you go to the right of this graph. But if you're content with something which is a little bit less accurate, but it's much easier to use and train, then maybe you can pick a traditional representation, and that may be also better. Okay. And here you can see some different reconstruction we've got with this different method. So, IDR and Nerve, that are the ones that give you the best perceptual quality, are on the right. Let's see some more examples and more. So you can see you can reconstruct objects which are actually fairly complex, such as, for example, this bonsai plant. Okay. Again, this is because it's volumetric representation or implicit representation. They allow you a lot of flexibility in terms of modeling complex shapes, which is a good thing, but also one reason that my course were fit. Which makes me jump to my second task, which is harder than the first. So what we're going to do here is not to take a single video as input, but we're going to take all the videos in a category. Okay, it could be 1,000 videos or something, and our goal is to train a single model that reconstructs all of them. It's almost like a single NeRF or a single IDR that is somehow able to encode all these different videos or all these different objects and give you the reconstruction for each one of them. All right, so we're moving to a model that can capture not a single instance, but rather an object category. That's the idea. So how are we going to do that? Well, again, we're going to use an implicit representation for that. For example, NeRF. And NeRF gives you two things: gives you a function f and a function c. The function f is what tells you whether a given point in space is being occupied or not, whether the surface is found there or not of the object. And the function c gives you the color of, well, a bit more information actually, something about the gradients of that point in space, so you can render it. Okay, so that's what NeRF does, and many of these other methods also give you. Okay. Now this is good for one object, so you can train a single network or model that gives you f and c. But what happens if you want to have more than one object encoded? Well, the other thing you can do is to add to this function f and c another argument. So here you have x, which is the location of 3D point in space that, for which you want to get the occupancy and the color. What you can do is you can add another parameter z, which is a code that essentially encodes for the object shape and color itself. So this means that if you go from one apple to another, you don't need to train a new network. All you need to do is to change some parameters in your model, which are expressed here as inputs to the functions. Okay. Now this is a natural thing to do. And so again, what you do, if you take this route, this approach, you start from a lot of videos. For each one of them, you're going to have a code. This code will be injected into just, for example, MLPs, so that you can get occupancy and colors. And because you can tweak the code, you can get this MLP to give you the reconstruction of many different objects. So this is essentially an autodecoder, all right? Autodecoder means that you optimize during training of an optimization process the code that you require for the construction of each individual video. So this is a learning process that is required, if you like, to get the code. You don't get instantaneously. You do not get them instantaneously as you would if this was an autoencoder instead. Nevertheless, it is a way of testing the capacity of a model like that to capture these objects. Okay, so here you see some other examples of that, and now you start to see that things are a little bit different. In this case, NeRF does not work as well as other representations. Okay, so NeRF is really good for a single scene, but at least in our experiment, it was not as good in terms of capturing a large number of different objects in the single model. And here's more examples of that. So from these videos, you should now probably have noticed that SRN is a method that works very well for this task. So what's that? Well, this is a method that uses LSTM for remarching in the volume of space that you want to render. So it's not using an MLP like NeRF. It's not using a sine distance function. It's just using a complete neural representation of the volume, which is learned in a way that also the remarching process, this process of looking through the volume to render an object, is learned as well. All right. And so if you look at the actual measures here in terms of the reconstruction quality, visual reconstruction quality, and shape reconstruction quality, you see that this is actually true. It is from in the metrics as well. For this particular task, SRN actually turns out to work the best. Okay. Now I'm going to move to my last task here, which is even harder. So what we're going to do now is we're going to divide the process in two steps. First, I'm going to use a lot of videos to train a model of the object category. Okay. And once I have this model, once this has been trained, what I want to be able to do is to take a small set of images, for example, say 1 to 9 images, and instantaneously, in a feed-forward manner, get a reconstruction of the object. Okay, so now we're moving into a regime in which we have learned something about an object category in pre-training, if you like. And then now at test time, we're given some examples of views of an object, and we want to get more or less instantaneously a 3D reconstruction of it. In fact, not just that, but also the ability to render the object from new views. So that could be useful for graphics. Okay. Now we could use, so before we have seen this auto-decoder idea, and maybe we can just start from that and try to slap something on top that makes it work for the case in which we want to have a fit-forward solution for the construction. So what we need to do is somehow to come up with a value for our code here, Z. So maybe the simplest thing to do is to say, all right, here's my input image. What I'm going to do is going to apply an encoder, which is itself a network, for example, CNN, that given the RGB image here, gives me the code Z that I need to use to put into this model to get the reconstruction, right? Straightforward, right? So you just learn an autoencoder effectively in this way. And if you have more than one image, maybe you can just pull information from many images and somehow combine them into a single code so you can get a better reconstruction. So that would be the naive plan, and you can try, but it doesn't really work very well. So there's a bunch of problems, but one of them is if you base your supervision on the output of structure from motion, what you're going to see is that once you reconstruct your object from these videos, you're not going to get them aligned. So there is no canonical shape or no canonical reference for reconstruction. So once you reconstruct those objects, they will all live in a slightly different, slightly misaligned space, if you like. All right. So if you then naively try to get a network to learn that, that doesn't make sense for the network, because the network is going to try to perform a reconstruction from an image. And if you supervise it with the geometry that you've got from structure from motion, well, that's completely ambiguous. Even if you put in twice the same video into structure from motion, the same exact videos, because of randomization in the way things are done, you're going to get different solutions. And now if you supervise your network to reconstruct that solution, specifically that geometry with that particular orientation in space, that does not make sense because the network sees the same images in this case because it's the same video. But because the ground truth now has changed, because it just reruns structure from motion twice, then this creates a sort of conflict for the network that cannot be resolved because the network only has images as input. It doesn't know anything about structure from motion and how that was done. All right. So there are ways around that. You could try to make the space canonical by aligning all these objects. But what we did was something different. So what we're going to discuss now briefly is two ideas, which might just well just get on with it. So the first one is as follows. We call this word conditional reembedding. And so here you see the comparison in math. So to the top left here, you see what Neuromorph would actually do. So Neuromorph is based on learning an MLP, a network, if you like, that takes as input 3D point X that you want to query and the code Z for your object, and gives as output the occupancy and color for that point in space. So what we're going to do is going to write some of the same equation, but instead of plugging into Neuromorph a dependency on X and Z, we're going to make the code itself depend on Z. All right. Now this may sound a little strange, but effectively the process can be described easily. So what we're going to do is going to start with an RGB image. We're going to extract some features using, for example, UNet. We're going to have a camera that we want to use for reconstruction, so from which we want to get a rendered view of the object. What we're going to do, because we know the alignment between the target camera and the input camera we want to render, we're going to go along this ray, and we're going to pick information for the corresponding points along this equipolar line. All right. So what this means is that the code, effectively, the code that we get for a point here is the code that you read out from this input image at this particular location, which is a point on the equipolar line, and the point which is obtained for a specific depth or distance from the camera from which you want to get your rendering. Okay. Now, this fixes the problem completely because the way you pull information is completely view dependent. It does not depend on the reconstruction you get from structure from motion or the absolute location of the geometry with respect to the camera. This is purely view based. So that solves this ambiguity that I was discussing before about how structure from motion does a reconstruction of those objects. And here you can see little videos that show you how this actually works in practice. So this is working. So these two would be two input views that we get for reconstruction. We extract features from them, for example, using a ResNet encoder. All right. And now suppose we have a target view that we want to render. So that's the image we want to get. So we're going to shoot rays through that. This will be in principle going through this volume, all right? And then for all those 3D points, we're going to look where they project onto these other images we get as input. Okay, and we're going to pull features from those locations. So they will. Those are the ones that form our encoding for that particular two-dimensional point. These encodings are aggregated based on the viewing angle. That makes sense because you want to get, well, it doesn't make sense to use certain views for certain points because you're going to have an occlusion. And that is what goes into the MLP instead of what usually goes into NeRF. Okay. And so that's allow you then to do to get your rendering done. So here you see a couple of reconstruction that were obtained in this by this method. So you see on the left 3 frames that were given as input, and then in a feed-forward manner, this process gives you the new views that you see on the right. Okay. And here you see some reconstruction as the object turn around. Now this is actually a lot better that you can get if you don't have this kind of embedding. Pretty much if you just use standard NeRF, this wouldn't just work at all, all right? But you can see that there's still quite a lot of artifact. So I'm going to explain in a minute how you can improve on this as well. But if you compare NeRF with and without this style of embedding, you see that there's a huge difference in performance. Okay, so what about this improvement that I promised? Well, that's our latest paper. Actually, I'm not an author of that, but I'm going to present it anyway because it's a follow-up to this previous work, and this is actually where we introduce new data set of objects that that's going to be made available to you in a few days. So there are some limitations with the method that I just discussed. So as I just mentioned, this process is very similar to NeRF in that you go through this volume of space, and then for each point here, you want to measure or have an estimate of occupancy and color. The way you pull information from there is to go you're going to essentially look at specific points, which are dictated by where you are in space in those images. So this process is not really able to reason about the information you collect along the range. So information is pulled in a very simple manner for an integral, but there is no logic that allows the method to actually reason about all the points you visit along the array in order to determine the color you see here. Or if you like, there is, but it's a very simple integration process, which is, good enough sometimes, but maybe can be improved, perhaps to account for the fact that some of those points might not be available in your views. And so maybe the color has to be hallucinated as opposed to be sampled, all right? And the other thing which is a little bit not satisfying is the aggregation function. So here is where we take multiple views. So we combine the information that comes from these views together. So we get a reconstruction, all right? And this was, again, handcrafted. And maybe if we use learning, we could do something better there. And so how are we going to do that? Well, we're going to use transformers. So this is essentially a sequence of samples in space. If there is a sequence, then it's natural to use a transformer to pull information there. And so that's exactly the idea. Instead of just pulling the way NeRF does, we're going to use a transformer to do the pulling along the array. Okay? And what about the other direction, the other issue? The other issue is when you want to integrate not information along the array, but information across different views of the object. Well, we can collect this information, and that's going to be a sequence, if you like, but it's an order in that sequence. It doesn't really matter. The orders are arbitrary. But then you can use another transformer to pull along that dimension. Okay? And so this is essentially what this NeRF format actually is a combination of NeRF and transformer, obviously. And so the way this works is by applying a transformer along rays in one step, and then the next step is going to apply a transformer along the views instead. And you keep alternating this construction, all right? So you do a transformation, a transformer along rays, and a transformer along views, and this will essentially allow information to interact across views and spatial location as well. Okay. And well, yes, this turns out to work fairly well. So in some metrics is actually the best method we can use here. For the other examples so in order for the other methods to be even competitive with this, we have to modify them to use this word conditional reembedding that we have discussed. So this is what you see here in this slide. So this is SRN plus our prior work where we do this sort of word conditional reembedding. And if you don't do that, you get very poor results for this particular task. But if you do, then they tend to perform okay. But this transformer, because it's using these transformers, actually tends to work quite a bit better. at least in terms of perceptual quality. In terms of reconstruction error depth, actually, this is about the same or slightly worse in this instance of SRM with these warp embeddings. Okay, and so here you see some reconstructions. All right, I wanted to briefly mention something else, but there's really no time, so I'm just going to see what it was. There's another method that we're going to present at this conference. This is about learning correspondences between objects. This I think is very important though, because if you want to learn an object category, you got to have correspondences between different points. These methods don't really have a notion of correspondence, which is explicit, but for things like humans, which are deformable, they have a very well-defined structure, that is actually very important. So I'm going to skip all over this, unfortunately, but I think this is actually very interesting. So I invite you to have a look if this is a problem that could be useful for you to look at. And we have this network which we call Neuromorph that can take in a sort of completely photo manner two meshes and spit out an interpolation between them, as well as an alignment. This is trained in a completely unsupervised manner, right? And the best thing about this is that, let me skip over these lines. It actually performs better than stuff which is supervised. Okay, so it's a little toy, but works very, very well. And there's also a fairly elegant architecture. So if that's something that could be of interest to you, I strongly recommend to have a look. All right. Okay. So I think I'm out of time, so I'm going to just conclude. So summary for today. So I wanted to present you some of our efforts in terms of learning the object categories. I presented three things, or in fact, two things in a bit. The first one was a new data set, common object in 3D, which is going to be available next week, maybe the following week. And a certain study and a certain number of new methods to be able to reconstruct those objects from a very small number of views that could be actually very useful when it comes to interpreting a scene. And then finally, this task of correspondences that unfortunately I was not able to explain. But you see here funny videos of a dog being aligned to a man as the man does something. All right. Okay, that's all I have then. So if you have any questions, I'll be able to answer them.
Yeah, thank you. Thank you, Andrea. Pretty interesting talk. So since we're a bit out of time, maybe we can allow for one question, or maybe we can also feel free to discuss in the chat box if you're available.
Okay.
Yeah.
So I see there are some questions in the chat box anyway, but so let me know what to do.
Maybe you can just pick the first one, and then quickly reply to that, response to that, and then we can move down to the next speaker.
So you were. You were to answer a question here.
Yes. I think there's a question for WCRE. Do you use any test time optimization, or is it fully feed forward?
So in the last part, it's fully feed forward. Yeah.
Okay. Yeah. Thank you. Thank you for the short answer.
All right.
Yeah.
Cool.
Yeah. Maybe if you're free, you can also feel free to reply to them in the chat box.
All right. Okay. Excellent.
Yeah. Thank you.
Bye bye.
Yeah. Bye.